All right, let's look at identifying graphs of the function and its derivative. So here we have two graphs, and the red is our original function, and the purple or the solid line is our derivative, f prime of x. And you can see we had x to the half power square root of x, and then the derivative is 1 over 2 times the square root of x. All right, and here's another example of the original function and its derivative. And so what are some things, can we identify original function? And this one's probably a little easier. If you remember, the original function is, you notice the power is 1 more than its derivative. This one might be a little harder. You would have to convert this back to x to the 1/2, move it to the top. That would make it x to the negative 1/2, which would be 1 less. If I do 1/2 minus 1, that gives me a negative 1/2. So we can and look at the graphs of those and what they look like. So let's look at this function, f of x and f prime of x. So we have 9x squared plus 6x, so that is our derivative. Okay, so f prime of x is our derivative, and f of x is the original function. So you can look at here, and we're going to look at, what can we tell from these functions, or what do they let us know? Well, notice what's going on with our function as our original function. As you can see, it's coming up, and then it kind of goes down and back up again. And what's interesting, if you notice what our function is doing as well, okay, as our original function is increasing, then we get to a point where it's no longer increasing and it starts to decrease. Then we get to the point where it's no longer decreasing and it's going up. Well, look at our derivative as we get to, let's say, about this point right here. Notice the original function is increasing and our derivative is above the x-axis. Here's our x-axis. Then our function from there, our original function decreases till we get to here. And notice what my derivative, it's under the x-axis. So it's where our function is decreasing, that's where our derivative is under the x-axis or below the x-axis. Then our function starts increasing again, and look, our derivative is above the axis. So we can tell a lot from a derivative of what our original function would be doing. Okay, and let's look at cosine and sine x. And just by looking at, what is the derivative of sine x is cosine x. And you can see what these functions as well. If the red or the dotted line is my sine function, which is the original function, and look at our cosine, what it is doing. And again, as the sine increases, it gets to a point where it's no longer increasing, and you see that this is above the x-axis, the derivative is. When the derivative drops below the x-axis, that's where our original function is decreasing. And then the derivative goes back above it, and that's where our original function is increasing. So again, that tells you a lot about your functions. Your derivative does. One other thing to point out is if you look at the original function where it crosses the x-axis, on the derivative we have horizontal tangent lines. Same thing here. Where it crosses, we have a horizontal tangent line on our derivatives. So those are all things to keep in mind into some future things when we get there. All right. Here we can look at the image and change the function to a function then compare the graphs of the function and its derivative. And look and see, is it drawn correctly here? So that's something you can do, to play around with it and see how you change the function. How's that change the derivative? So here we have 2 raised to the x power, and so the derivative of that would be 2 to the x ln 2. And let's just change this to something, start with something simple. Let's just do x squared. And now we're back to, this is what we've seen before. Again, the original function where it's decreasing, you notice the derivative is below the x-axis. Where it increases, it's above the x-axis. Where the original function, do you see it touches right here? That would be my x-intercept. And you can see, or where the derivative has 0, you can see that would be a horizontal tangent line on the original function. Let's look at something a little. What if I go to the 5th power plus 4? There it is. And you can see again, here's the derivative, which is 1 less. That constant goes to 0 when you're doing the derivative. So you can see the original function and what's going on with its derivative. So this is kind of neat to play around and look at functions and their derivatives. Okay, differentiability implies continuity. So let f of x be a function and a be in its domain. If f of x is differentiable at a, then f has to be continuous at a. Okay? So we want to show that f of x is continuous at a given f prime, continuous at a given f prime of a exists. So in other words, it's differentiable at a. So we're going to show that the limit of the function as x approaches a equals the function value at a. That implies continuity. Okay? Given f prime of a equals the limit as x approaches a of our f of x minus f of a, x minus a exists. And this is just a proof showing you that this is true, that that the function, if we show that if the limit of f of x as x approaches a equals the function value. So this shows us how it implies continuity. Okay, now here's an interesting question. Does continuity imply differentiability? So we're going to determine this answer to this question. We're going to consider a few counterexamples. In these examples, a function is continuous at a point, but it is not differential at that point. And all it takes is one example to make this false. You know, does continuity imply differentiability? So let's consider the absolute value function and x equals 0. So here we take the limit of the function as x approaches 0. And so you can see we've look at this. We have the limit of absolute value of x over x as x approaches 0. And when we look at this, okay, we break this down. Here we're looking at it from the right, and it's 1. And then when we look at it from the left, it's -1. And those are not equal to each other. Okay, so again, you look at it from the left and from the right, and you'll see the limit does not exist. Thus, it is not differentiable at x equals 0, but it is continuous at x equals 0. So even though differentiability implies continuity, it is not the other way around. Continuity does not imply differentiability. Now let's look at this as a graph. If you notice, an absolute value has a sharp point here, okay, a sharp corner. So the limit of the slopes of the tangent lines on the left and the right were not the same. One was +1, and one coming from this one was -1, this one was +1, and they are not the same. In other words, for the limit to exist, they have to be the same. And so they have to be smooth, continuous, and smooth. We need not a sharp corner, but it has to be smooth. So derivatives and continuity. So let's look at this cube root of x, and as x approaches 0. Let's look at the limit of that as x approaches 0 as we plug those in. And you can see as we kind of go through this limit process, we end up with the limit of x to the negative 2/3. And remember what it means. We pull that negative 2/3 down, make it positive. That's going to be the cube root of x squared. Well, we need to look at this because if I directly substitute that in, I get 0. So we need to look at the limit from the right side and the limit from the left side and see where they're going to. If we look at this graphically, we'll get to see here in a minute that the limit doesn't exist as x approaches 0. Thus, the function f of x equals the cube root of x is not differentiable at x equals 0, but it is continuous at x equals 0. So remember, this is infinity, not a real number. So it doesn't exist as far as we're talking about right here. This ends up being a vertical tangent, and these are sometimes hard to figure out or hard to know. The function fails to be differentiable at a point where there's a vertical tangent line. So that would be a vertical tangent line at this point. And so what's the slope of a vertical line? It's undefined, and that's what we're seeing here, that the limit as far as a real number, it doesn't exist. Okay. So for the graphs below, determine for which values of x equals a, the function is continuous but not differentiable at x equals a. And if we look at the first one, I don't see any sharp corners. Okay. We're looking at this function, and I don't see any place where at no value of x, again, the function is continuous but not differentiable. Okay, so at the places where it's continuous, it looks like it's also differentiable. Excuse me. If I look at the other one, though, we do have a sharp point at 2. So there it's continuous, but it's not differentiable at that point. These other places, it's not continuous, just like over here. But this one, it is continuous, but because of that sharp point, it's not differentiable at that point. And we also look at piecewise functions. That's continuous and differentiable. A toy company wants to design a track for a toy car that starts out along a parabolic curve, then converts to a straight line. The function that describes the track is to have the form below. For the car to move smoothly along the track, the function f of x must be both continuous and differentiable at -10. Find values of b and c that makes f of x both continuous and differentiable. F of x and x are in inches. So let's take a look at this. For the function to be continuous at -10, the limit has to exist, and it has to be the same as the function value at -10. And that's what this first statement is telling us. The limit must exist and be equal to the function value at -10. So how do we do that? Well, we look at the limit from the left side. Okay, and the limit from the left would be 1/10 x squared plus bx plus c equal to 10 minus 10b plus c. So we will substitute this in. Okay, and we get 10 minus 10b plus c. Okay. Then from the right side, again, we look at the same thing, and we get 10 over 4 plus 5 over 2. So again, we plug in our negative 10. We end up with 5. Thus, we know that 10, or in order to get what we need, 10 minus 10b plus c equals 5. We solve this for c. C equals 10b minus 5. So for the function to be differentiable at x equals a negative 10, remember these must exist and be equal to each other. And you can see this is pretty complicated using our limit definition of a derivative, but we're going to plug these in and see what we get. So we plug in our f of x, we plug in our f of negative 10 that we figured out, or that we've come up with, and run through our simplifying these functions. As you can see what we're doing here. And remember from the previous slide, we had c equals 10b minus 5, so that's where that comes from. And we have to simplify this. We use the quadratic formula. Again, this is pretty ugly, but we end up coming, and you may want to pause this to look through this to see each step, but we end up knowing x equals negative 10, x equals, and here we can say negative 10b plus 10. Remember, you get two answers from here, plus or minus. So we end up with 10 and 10b plus 10. We're not done yet. And work through the rest of the problem by simplifying. Here we're looking at it from the left side. We end up with b minus 2 equals negative 1/4. So b ends up being 7 over 4. We know c, so now I can substitute my b into that 10b minus 5 and come up with 25 over 2. So, after all of that, this is what b and c would have to be in order for this to be smooth or continuous and differentiable, or continuous and smooth with no points. Now that took quite a bit to get there, to get those calculations, but that's what it would take to figure out what are we going to need to keep that smooth and differentiable.